Hello everybody, I am Vimal, working as an assistant professor in CUC College of Engineering Coimbatore. Now I am going to explain about Otto Cycle. It is a gas power cycle for operating SI engine, that is fast ignition engine. Coming to the introduction, what is an engine? Engine is a device which transforms one form of energy into another form. Especially heat engine, which converts chemical energy from fuel into thermal energy and utilizes it to perform useful work, that is mechanical energy. Coming to the classification, the heat engine is broadly classified into two types. One is internal combustion and another one is external combustion engine. Internal combustion engine is again classified into two types. One is rotary engine and another one is reciprocatory engine. In the rotary engine, we will be coming across the SI engine, that is fast ignition engine. For all the gas power cycles, we are having Carnot cycle as the ideal cycle. We have found the assumptions are that the working fluid is gas for the gas power cycles. The air undergoes a thermodynamic cycle, even though the working fluid in the actual power system does not undergo cycle. We approximate, we approximate the we approximate the cycles with the following assumptions. The air continuously circulates in a closed loop and always behaves as an ideal gas. All the processes that make up the cycle are internally reversible. These are the two assumptions what we made in gas standard assumptions. Coming to the terminology, some of the terminologies what we use in the SI engines are TDC, that is top dead center, and BDC, bottom dead center. When the piston in the cylinder goes to the topmost position in the cylinder, it is known as the TDC. When it goes to the bottommost position, it is termed as BDC. The distance between the TDC and BDC is termed as stroke. The diameter, that is the diameter of the piston or the inner diameter of the cylinder, is termed as bore. Then coming to clearance volume, when the volume above the TDC is termed as clearance volume, and the volume raised out by the piston from TDC to BDC is called as displaced volume. Then the another terminology is compression ratio. Compression ratio is nothing but the ratio between the maximum volume to that of the minimum volume formed in the cylinder. That is, it is represented by the symbol R. R is nothing but V max by V minimum. Then there is another terminology called as mean effective pressure. Actually, it is an imaginary pressure, that is the average pressure which is created when the piston during the entire power stage will produce the same amount of net work as that produced during the actual cycle. This is the PV curve for the Otto cycle. When the piston moves to the topmost position, it is called as TDC, and when it moves to the bottommost position, it is called as TDC. Between these two centers, the volume is termed as displaced volume, and the length is termed as stroke length. This is the formula for calculating the mean effective pressure. This is the pictorial representation of 8-cylinder 4-stroke internal combustion engine. The four processes which are involved in the Otto cycles are: first one is intake stroke, another one is compression stroke, third one is power stroke, and the final one is exhaust stroke. Okay. Coming to the first stroke is the intake stroke. Here the piston moves from TDC to BDC. During the time, the process intake stroke will take place from TDC to BDC. After that, the compression stroke will take place. During this time, the gas is compressed, or the air mixture is compressed isentropically from BDC to BDC. After that, the third process, that is, at the end of compression, ignition will begin. After ignition, the power stroke will take place. This ignition is considered as constant volume heat addition. followed by the expansion stroke or the pop-out stroke. During the time, the piston moves from CDC to BDC. Then finally, the exact stroke will take place. Here, the heat is released at constant volume to the surrounding. That is constant volume heat rejection. This is followed by, once again, the cycle returns to the intake stroke. Thus the cycle is completed, and once again another cycle will take place. The first process, that is suction stroke, 1 to 2. The process 1 to 2 is termed as isentropic compression. Process 2 to 3 is termed as constant volume heat addition. And process 3 to 4 is isentropic expansion. And 4 to 1 is constant volume heat rejection. Okay, now we are going to find the thermal efficiency of the Otto cycle. Thermal efficiency is nothing but work done by heat supplied. Work done is nothing but the net difference between the heat supplied and the heat rejected. Subtracting these two, we will be getting 1 minus Q out by Q in. So we are trying we obtain 1 minus Q out by Q in. That is heat supplied, net heat given to the system divided by heat supplied. Heat supplied is nothing but mCp Cv into del T. Cv is nothing but specific volume, Cv. Mass, this is mass, this is Cv is nothing but specific heat at constant volume. Specific heat at constant volume. mCv T4 minus T1 divided by mCv T2 minus T2. So we are introducing the compression ratio into the thermal efficiency. That is, we are the common terms will be cancelled. That is, we are cancelling mCv in the denominator and the denominator. Finally, we obtain 1 minus T4 minus T1 divided by T3 minus T2. Taking the T1 from numerator and T2 from denominator outside. We know that in isentropic compression, the relationship between the temperature and volume of T2 by T1 is equal to V1 by V2 whole plus K minus 1. And V1 by V2 can also be written as is nothing but the compression ratio. V1 by V2 is compression ratio, that is R. Similarly, V4 by V3 is nothing but compression ratio R. So these two terms are same for both that temperature ratio. That is T2 by T1 is equal to T3 by T1. That is this equation. Or it reverses. So we can term the equation number 1 as, we can convert this one term as 1 minus T1 by T2. Okay. Then 1 to 2, that is isentropic compression can also be written as N by R. In terms of R, we are converting it, where the compression ratio is R is equal to V1 by V2. That is, we get the final equation for the isothermal efficiency of the Otto cycle as 1 minus N by R per K minus